Okay, let's start. So today we're going to learn a new algorithm. It's called BLAST, spelled as Basic Local Alignment Search Tool. So this algorithm is used for database searching. So for database searching, we want to discover or verify the identity of newly sequenced gene. So if you clone a gene, you sequence it, but you don't know what function it is or what group of gene family it belongs to. So we can use a BLAST to search. And also, like I said, you can find out which member of the gene family it belongs to and classify the group of genes. So this is the purpose we're doing the BLAST search. But last week, we learned about alignment, if you remember. So one algorithm for the local alignment is the Smith-Waterman algorithms. So naively, we could use Smith-Waterman algorithms to compare the query sequence to a database sequence, like the sequence you can find in GenBank. Okay, so we can use that and find out the similarity between the query and the database. But there's a problems because the database are huge. So the GenBank sequence database, they're too big. For example, it's a kind of old data, but we have 82 million sequence. So you remember when we do the Smith-Waterman comparison, the complexity or the task of the comparison is a very huge task. Okay, it's intractable. So we cannot use Smith-Waterman to find out the similarity between the query and the database just because too big. There's some solutions. Use heuristic approaches. So the heuristic means we find some shortcut to find the solution, but it will not guarantee the solution is the global optimal, is the best one. But it's a good enough solution. So there's always a trade-off between the sensitivities and the speed. Okay, so this is the two algorithms that are used for the database searching. An older one called FASTA. So the one we're going to talk about today is BLAST. So the take-home message for this slide is the Smith-Waterman is slower. It is slower, but it will guarantee you find the best, the optimal solution. But it's too slow. So the questions, the biological questions for this algorithm is to find a sequence with a similar pattern in a library of database. And the data we need is include the query sequence, the sequence you cloned, and also you need compare that to a database. So the common database like a BLAST or EMBL. An algorithm I'm going to introduce to you is the BLAST algorithm. So what is a BLAST? There's a definition. So it is an algorithm for comparing primary biological sequence information. So it's compare sequence of the query sequence to a database. It is a heuristic approach. Okay, put more emphasis on speed. So it's reasonably fast and find a good enough solution, but it's not optimal, the global optimal. Okay. So there's a few terminology. I'm going to go through these. Don't worry if you don't understand all of them. We're going to show you more details. Okay. So for doing BLAST, it will find out segment pairs. The segment pairs is a pair of equal length substring of sequence 1 and sequence 2. So for example, the sequence 1 is from the query sequence. Sequence 2 is from the database. So the segment pair is part of the comparison that between these two sequences. And locally, a maximal segment pair is the segment pair whose alignment score cannot be improved by extending or shortening it. So we will see how this algorithm works. But this means if we compare a partial sequence of two sequence, we find some similarity in part of the comparison. When you extend this comparison, it will not improve the score. We call that local maximum segment pair. Okay. And it's similarly, this is the maximum segment pair, which means we look at all the segment pair, find the one with the largest score. Okay. So this is the terminology. And the BLAST is attempt to find all database sequence that when paired with query sequence contain an MSP, allow some cutoff S. Okay, so when we do a BLAST, we have one query sequence and we have a database sequence. In the database, there's millions of sequences, could be from different species or different genes. So the objective of the BLAST is trying to find all of those sequences in the database which contain a MSP with a query. You following what I've been talking about? So, OK， 这个 BLAST 它的这个目标就是通过比较你的 query sequence，query 就是说你的基因你要寻找的这个基因和一个 database，database 就是你这个数据库，OK， 可以是 GenBank 或者是其他数据库。然后它的目标就是什么呢？就是找到这个基因。找到这个数据库里面所有的这些序列，你数据库里面有很多几百万的序列，所有的序列，这个序列当中和这个 query 有一个这个 MSP 的，把这些序列找出来。当你做 BLAST 的时候，它给你返回的就是这些序列。那这是它的一个这个BLAST 的 algorithm 它的目标。那我们下面看看他们是怎么做的。OK，so these segment pairs are called HSP. And also, they have some cutoff score, S. So the S is chosen so that it's unlikely comparison of query sequence to unrelated sequence. So you need to have a cutoff score. So if the score is less than this one, we will not consider that a related sequence. 就是你做 BLAST 的时候，你需要有一个这个分值作为一个叫什么标准吧？如果比这个分值低的时候，你就不考虑它了，因为两条序列中间它总是有一些地方相似度，相似度太低就不考虑了。Okay. So this is the goal of the BLAST algorithm. Okay, then how it works. So I'm going to go through all this text first. Then I'll show you some cartoon, some graphs, how it works. So for the first step. Remember, for the BLAST algorithms, it always tries to find some shortcut to speed up, to make the searching fast. So let's see how it do that. So first, it will choose the length parameter W and the threshold parameter of T. Okay, it will find hits or a W length substring in the database that align with the word from the query sequence with an alignment score greater than T. So what does that mean? Let me show you a graph here. Okay. So say this is our query sequence, the sequence we want to compare to the database. So you can set up a length of the word length. So here we say 3. Okay, so you're going to chop your sequence into a piece of substring, the length of 3. So we have PQG, QGE here, and GEF here. And you can go for the rest of sequence, like EFG, okay? So you find out all these substring, and then we will calculate all possible match to this substring. For example, for PQG, so we could have PQG in a database which match exactly as the query. Okay, so then you calculate the score from PQG match PQG. So how to find out what the score it is? Usually for the BLAST, for protein sequence, we use the BLASTM matrix. So this is the matrix. Remember, we do the sequence alignment. We also have a matrix. Yes. So this is for the protein. So, for example, if you have a C matches C, it will have the score 9. Okay. If you have C matches S, so all these are 20 amino acids. So you have a different number. So all these number will calculate from known gene families. So this number are calculated from independent data. So we have these metrics. Okay. So now we can use this to find out the score. So we have P and P here. You can we can see where's the P? Oh, P is here. Okay. P matches P. So we have a score 7. So this is 7. And Q matches Q is 5, right? And this G matches G is 6. So the total score of exactly match of PQG is 18. Okay. Correct? Okay. But you can have other, not exactly match, but similar. So if we have a PEG matches PQG, so we can find out PM matches P is 7 and E matches Q. Okay. Q matches E here is 2. So 7 plus 2 plus 6, so 15. So the first step they will do, they will find all combination of these 20 amino acids for 3, the length of 3, and try to match the PQG and calculate the score, right? So how many possible sequence we could have for length of 3 from the 20 amino acids? How many possible? So we have 20 amino acids, and if we say we have a length of 3, a protein of length of 3 with 3 amino acids, how many different of that sequence we could have? So it's 20 times 20 times 20, right? So we could choose one from these 20, put it on the first side, and another random pick from this 20, put it on the second side, okay? Right? So we have 20 times 20 times 20. So that's a big number. So we can calculate all these values. So 20 times 20 times 20, 3 amino acids, and compare to the PQG and calculate all this number. So we have a list of possible match. Any question of that? Okay, I explain in Chinese. 那么我们这里这第一个是 PQG， 然后我要和它和任何三个长度的这个氨基酸去比。那么这个蛋白质吧，那个一共有20种氨基酸，那么一共有多少种这个3个氨基酸的蛋白质？这么小的蛋白质吧，一共有多少种？对，20乘20乘20，对吧？那么就把这些所有的跟它全部比，把它分子全部计算出来 ，OK？ But then we have too many of these small piece of amino acid sequence. But remember, here we have a so here we have a score. So we set the alignment score has to be larger than T. So for so many 20 times 20 times 20 possible sequence, there's only a few score larger than T. So that's only the one we're going to keep. That's we will have less word to check in the later stage. Okay. So this is the first step. So first step, we choose a length parameter W and threshold parameter T, and then we calculate all these similar words in the database compared to the query. Okay. So that's what we did. Make a list of all words in the query sequence of length W, and use the Blossom matrix, calculate all the scores. But because the score, we have a set that have to be larger than t. So although the total possible numbers is bigger here, it's 80,000, but we said the score has to be larger than a threshold. We tell it, so it's only a few words we're going to check in the later stage. So this is how it's going to work. So the first step would use the seedling. So we just calculate all these possible matches, as I said. And then we search the database, use a search tree-based method to rapid compare to the database. What does that mean? So for example, so if we look at the first word, the PQG, and after we calculate all of these, say we only have these 3 left. All the other possible because it's less than 10, so we don't keep them. Okay. So we only have these 3 sequences left, and we check if these 3 sequences in any of the sequences in the database. Okay, so we just check this sequence, see if it is in the database. And to make it fast, it will use a search tree-based method. So we're going to revisit this later when we do the mapping for the next generation sequencing. When we do the mapping or do the assembly, so it can also use the search tree-based method. It will make things fast. Okay. 就是这里呢，前面我们就找出来和那个我们前面那个3个氨基酸的那个序列，对吧？和它相似度比较高的，按照前面这个例子的话，我们可能留下了这3个，对不对？和它相似度比较高。那么下面一步就直接在这个数据库里面去找找哪一条序列当中含有这3个氨基酸序列的。那怎么找的话，它用一个这个 search tree-based method。它首先把你的数据库里面的这些数据，它按照这个氨基酸的序列，它建成一个树的形状，那这样它找起来会比较快一点。那我们下次以后做这个 mapping 的时候，给大家我们还会去看这个 searching tree 的 method。So with this implementation, it will find the seed very fast. Okay. So for example, here, so first we've cut up the query sequence, use this for seedling, and search this in the database. We find all these hits in different sequence. But some of the sequence, for example, have multiple hits. So this sequence has multiple hits, and it has a small gap here. So 2 hits that are not too far from each other. But for some sequence, the gap is very big. So we're going to feed out those sequences with a gap too big, or these sequence only with 1 hit. So this is the gapped blast method. So after the filtering, we only have this one left. So for the next step, so we try to extend the hit regions. So for example, so this is the sequence with hits of these seeds. We try to extend for other direction, both direction, to see if there's more matches between the query and the database sequence. And we'll extend this until the score drop off. So when we extend it, we may have more matches. It will increase the score, but until there's no more increase in the score, so we will stop extending the alignment. So that will be the result. One of the hits we find in the database. So this is the sequence alignment. And after that, we need to do a validation. So because the similarity between the query sequence and the database sequence, it could mean some biological significance. So which means those sequences are from the same gene or do the same biological function. But sometimes they just randomly have some similarity due to the randomly match. OK， 就是假设我们找到了这个 query sequence 还有这个 database sequence， 它们的找到了这个相似度比较高的这些序列。那这些相似度呢，它可以是因为它们是属于同一个基因，对吧？有同样的功能，还有可能它们仅仅是因为这个随机的一些相似性。比方说，如果我们说那个氨基酸的话，如果我们说 DNA 的话 ，DNA 只有 ATCG 只有4种这个碱基。你如果随机的拿2条序列的话，它们总是有一定相似度的。那蛋白质也是一样，蛋白质虽然这种可能性会低一点，所以这里的话我们要做一个 validation。That's why we need to do a validation. So the validation means we need to check if this similarity is significant. It's not just randomly matched. Okay. Okay, so, here's an example. So how we do the seeding. So first, we calculate, for example, this is our query sequence, and this is 2 sequence from the database. So after we start with the seeding, so we find in this first sequence there's matches of 4 seeds here. In the second sequence, also there's two matches. Okay, but because there's the distance is too large here, so after the filter, so we're not going to take this sequence because this gap is too bigger. It's greater than the threshold we set. So we only left with this one. Okay, so after seeding, so this is seeding. After this seeding, we're going to extend at both directions between the query sequence and the database sequence. So there's some mismatch and more matches and some mismatches. So the score will increase if we extend them, and until to a certain point, there's less match between the query and the subject, the score will drop. So then we will stop at there. So for example, so if we extend from this red region, okay, from this red region to the both end, until now we have a score 88. But if you further extend it, if we extend more, because all here is a mismatch, there is mismatch, we'll have a smaller score. Okay, the score will drop. Then when we stop, we will pick this one as the final result. So we will pick this one and report that. We will report this sequence from our database, and also we will report the alignment. Okay, any questions till now? 有没有什么问题？前面讲的这些步骤有听明白没有？什么地方不清楚？ OK， 这第一行这里就是说，我们是从这里开始往两旁边延伸嘛，然后你计算它的分数。OK， 这里的分数是这么高的，然后到这里的话，我们如果继续延伸的话，因为这里有很多是不一样的 mismatch， 那么你计算的分数它是会降低的。如果分数降低了，我们就不会继续延伸了。延伸的标准就你延伸一个，你计算一个分数啊。比方说，我前面计算，假如是78，它分数增加了，我就继续延伸了。就是你往两旁边扩展的话，延伸的话，如果分数增加，你就继续延伸；如果分数降低了，你就停止了。那么这里只是用了一个例子，这里它是88，这里继续延伸了，它分数比它低。那当然你是一个一个的延伸，这里是没有 gap 的。上面这个是数据库的，下面这个是我们的。这个上面下面哪个是数据库的都没关系，就是说两条序列。我们可以说是，上面是数据库的，上面是数据库的，下面是我们的那个是你的序列要去比对的序列。它就是分数降低了，它就停止了，不会是越来越低啊。这个 i 和如果你延伸的话 ，OK， 比方说这里是 i 和 i， 然后let me see，OK， 这里是 p 和 p，s 和 r， 对吧 ？s 和 r 它虽然不是完全一样的，但是它可能分值是大于正数的，然后 s 和 s 也是有 match 的，所以说它刚开始的时候可能会增加的，直到后面的话，它相似度差异比较大了，它就停止了。Any questions? The previous slide. This one? Okay. So the score PQG. So the PQG here means, so this is the query, and those are possible sequence match with the query. So the PQG here means we have exact match. So we have P match P and Q match Q and G match G. Okay, so for P, match P, we can find the score from this Blossom matrix. So this is the P, and that's a P. We just look in this table. If we have two P, it is 7. Okay, if we have two Q, we have a Q match Q. If we have two Q here, the score is this one. Okay, 5. And if we have G match G, the score is 6. So you add them together. So that's a score means we have exactly match. But sometimes we don't need to have 100% match. So if we have PEG, so we have P and P and Q and E. So Q and E is not 5, it's a 2. And G match G is 6. So that would be a 15. This is how we calculate the score. Those score means any possible amino acid sequence that can match those seeds. Did I explain that clear? Okay, so for a length of 3, so we have 8,000 possible amino acid sequence. But from these 8,000 of them, only 3 of them has a match score greater than 10. So, for example, theoretically, okay. So all the others, we don't have to consider them. So we don't have to consider those. We just check if any of these 3, if we can find that in a database sequence. So we have a fast way to do that. It's like tree, searching tree. So we check, for example, if we have 1 million database sequence, in the database we have 1 million sequence. So we see if the first sequence have PQG PEG, and PFG. If the first sequence has any one of that, so we put a seed there. If the first sequence doesn't have any of these, so we just don't look at them ever. So in this way, we can have very quick, very fast way to check through all the 1 million sequences in the database. So that's how it works. Okay. So So that's how we find out which sequence in a database is similar to the query. But then we need to evaluate. Like I said, we need to evaluate if this similarity is due to some biological significance or it is just random. So then we need to calculate a score. So you're all familiar with this one, right? So this is like the score when we do the alignment. Okay. So we have a score for the match, a score for the insertion, and a score for deletion, the gap, for the gap opening, and the gap extension. Okay. So it's very similar to the scoring metrics we use for alignment. But we need normalize the score, because that score, let me see this first slide, because this score not only dependent on the scoring metrics, not only dependent on these parameters, it also depends on how many sequences you compare to. Okay, so if the database is very small, so we will have a very small chance to have a match randomly. But if the database is huge, you will have a chance to match them randomly. Okay， 就是这里算出来的这个 score，R score， 它除了受这些参数影响的，但实际上它还不能够反映我们找到这个相似性是不是有意义。因为这个相似性的话，除了这个 score 这些参数之外，还和你比较的那个数据库大小有关系。假如你比较的数据库很小，那么你能找到一个随机的和你这个序列相似的这个可能性就比较低。假如那数据库无限大，那不管你什么序列，我都可以找到一个随机的和它相似的，对不对 ？Okay, so we have to adjust that. We have to normalize that with the size of the database. So this is the normalized score. It is the function looks like that. So the lambda here is the scale factors convert pairwise match score to probabilities. Okay, and the k is a proportionally constant to correct the number of sequence comparison. Okay, the k is a constant, but the lambda is used to convert the score to a probability. So that means. So this is a function, but it has a very solid statistic background. So they find out, there's a paper, find out the probability of the score matching between two sequences belongs to a certain distribution. So they use this to normalize it. Okay. So after the normalization, the S is independent of the scoring systems. So the S, after the normalization, the S is not dependent on the database, how big the database you compare. So that we can compare score between different systems. So this is normalized score. And there's even a better parameters, a better result. You can it's easy for human to understand. It's the E value. Okay. So when you do a blast search on the NCBI GenBank, so you will have a list of hits, sequence alignment. You will also have this E value at the end of the result, if you notice that. So the E value is expected number of alignments with given score would be found in a database by chance. So what does that mean? It is the expected number, how many times you can find the query sequence in the database just by chance, not because they are biological similar, or not because they have some significance, just by chance. 所以这个 e-value 的话，你如果做 blast search 的话，你可以看到后面会有个 e-value。这 e-value 是什么意思？这 e-value 就是说，你用这个 query sequence 在你这个 database 当中去比的时候，有多少你会发现多少个跟你这个 query sequence query 的序列是完全一样的，仅仅是因为随机的原因，不是因为它们之间有什么意义，生物学上的意义。随机的原因就是什么？就是说，比方我们拿一个序列10个氨基酸，然后我有一个就很简单嘛，10个氨基酸 ，OK，10个氨基酸的长的序列，每一个位置它可以取20种，对不对？可以取20种。那么我如果随机，我如果跟我这个 query 序列的话，如果随机的我从这个数据库中就能够发现有一个跟它一样的，那这个数据库只要有多大就可以了，20的10次方。如果我一个数据库，假如里面大家的序列都是不一样的，只要有20的10次方，那么你随便拿一个序列，不管你什么序列，我在这里面总能找到和它一样的这个序列，对不对？而且它是没有任何意义的，因为它是随机就可以了。所以这个 e-value 就是这个。假如你做完那个比对之后，这个 e-value 就是告诉你，在这个数据库当中，你随机的和它相似的可能有几个。Okay, then my question is, so do you think whether the e-value should be larger or smaller if you have significant hits? You think the e-value should be better, should be a bigger number or a smaller number? So if you have a significant hit, do you think the e-value should be a big number or small? Yes, small. Yeah, like I said. So the e-value is the number of sequence you can observe just by randomly. So if it is very small, it means it's not random. It means your sequence is significant. Okay. So that's why when you do blast search, we often set the e-value has to be less than a 10 to the minus 6 or a very small number. So this is e-value. Okay, so yeah, this is even smaller because if you compare a protein sequence, the e-value should be even smaller. So it's between 10 to minus 10 or 10 to minus 20, which could suggest your sequence is significant, has a significant hits. And there are also different blast search tools. So if we go to GenBank, I don't think we have a web internet connection. But if you go to GenBank, how many of you have used the GenBank blast search before? 你们有没有人做过这个GenBank blast search? Okay. So when you go to the GenBank, so you find the web page for the blast search. So how do you do? How do you search for your sequence? Mm. 对，就是说，因为它这个都是做了成了 web server， 然后你把你的序列连贴进去，然后你选择你是氨基酸还是蛋白质。那么你如果选氨基酸还是蛋白质，那这里它就会还有其他让你去选。就是我们一般做的时候，可能你不注意哪些参数怎么选，但实际上里面有很多参数。So if you blast nucleotide to nucleotide, so there's different algorithms. The common one is blast N. The N means nucleotide. Okay. So the query could be nucleotide. The database could be nucleotide. But if you want blast the nucleotide to protein, so we can use blast X. Okay. So to blast X means it will translate your nucleotide sequence into amino acids, into protein, and at 6 different frame of translation. It will translate, try to translate the forward strand and the reverse strand, all 6 frame, and then use those to blast the protein sequence to find if there's a significant hit. There's also, it's a T-blast X, okay, a T-blast N. So it can translate the protein to nucleotide and blast that to nucleotide. So it's depend on what kind of sequence you have and what database you want to blast to. So you can select all these different tools on the GenBank Blast web page. But there's a more, so this is easy to understand， 对吧？刚才前面我说的就是，你做 blast 的时候，你有可能是氨基酸的序列，有可能是蛋白质序列。假如你想用这个氨基酸叫什么？说错了。假如你想用这个 DNA 去比 DNA 的话，你可以用 blast N。你如果想用蛋白质比蛋白质的话，你用 blast P。如果你想用这个DNA 序列去比它那个蛋白质数据库的话，它上面可以选T-blast X， 它可以把你的 DNA 的序列给它翻译成氨基酸的序列，然后去比那个蛋白质的数据库。Okay, so this is easy to understand.